Time only moves forward because the universe is dying. Slowly, inevitably, every breath you take, every step you walk, every thought you think, pushes the universe closer to its end. This isn't philosophy, this is physics, the second law of thermodynamics, and it explains why eggs break but never unbreak, why you age but never get younger, why everything eventually falls apart. Let me ask you a question. Have you ever dropped a glass? Of course you have. It falls, it hits the ground, it shatters into 100 pieces. Now, have you ever seen those pieces spontaneously jump back together and reform the glass? No, never, not once in your life. Why not? The laws of physics don't forbid it. If you filmed a glass shattering and played the video backwards, every single motion, every trajectory of every piece of glass would obey Newton's laws perfectly. Momentum would be conserved, energy would be conserved, all the fundamental laws would be satisfied. And yet, it never happens. Glasses break, they don't unbreak. Eggs scramble, they don't unscramble. Ice melts, it doesn't unmelt. People age, they don't unage. Why? Because of entropy. Entropy is a measure of disorder, of randomness, of how many ways you can arrange the pieces of a system. And the second law of thermodynamics says, entropy always increases. In an isolated system, disorder always grows, never shrinks. That's it. That's the law, and it's the most fundamental, most universal, most terrifying law in all of physics. Because it means the universe has a direction, a flow, an arrow, the arrow of time, and that arrow only points one way, forward, toward more disorder, more chaos, more entropy, toward the heat death of the universe. Let me show you what I mean. Entropy is one of those words that gets thrown around a lot. People say entropy when they mean chaos, or disorder, or decay, and they're not wrong. But let me give you the precise definition. Entropy is a measure of the number of possible microscopic configurations that correspond to a given macroscopic state. Okay, that sounds complicated. Let me break it down. Imagine you have a box. In the box there are gas molecules. Let's say 1,000 of them. Each molecule has a position and a velocity. That's the microscopic state, the exact configuration of every single molecule. Now, the macroscopic state is what you observe. The temperature, the pressure, the volume. You don't care where each individual molecule is, you just care about the overall properties. Now here's the key insight. There are many different microscopic configurations that give you the same macroscopic state. The molecules could be arranged this way, or that way, or a million other ways. As long as the temperature and pressure are the same, you can't tell the difference. Entropy is a measure of how many of those arrangements exist. If there are lots of possible arrangements, entropy is high. If there are only a few, entropy is low. Let me give you an example. Imagine all the gas molecules are in one corner of the box. That's a very specific configuration. Low entropy. Now imagine the molecules are spread out evenly throughout the box. There are vastly more ways to arrange the molecules so they're spread out than there are to arrange them so they're all in one corner. So the spread out state has higher entropy, and here's the second law. If you start with the molecules in one corner and just let them move randomly, they will spread out. They will never spontaneously all gather back in the corner. Not because it's impossible, but because it's overwhelmingly unlikely. There are so many more ways for the molecules to be spread out than to be gathered together, that statistically, you'll never see them all end up in the corner again. You could wait 1 trillion years, 1 trillion years. It still wouldn't happen. That's entropy. That's the second law. Systems evolve towards states with higher entropy, more possible arrangements, more disorder, and once you're in a high entropy state, you're stuck there. You're not going back. Let's go back to the egg. You crack an egg into a pan. You scramble it. The yolk and the white mix together. They blend. They become a uniform yellow mess. Now, can you unscramble it? Can you separate the yolk and the white back into their original states? No. Why not? Because scrambling increases entropy. When the egg is intact, the yolk and the white are separate. That's a low entropy state, a specific configuration. When you scramble it, you're mixing the molecules. You're creating vastly more possible arrangements, high entropy, and the second law says entropy increases, You can go from low entropy to high entropy, but not the other way around, not spontaneously. Now you might say, wait, I can put things back in order. I can clean my room. I can build a house. I can organize molecules. True, but here's the catch. You can decrease the entropy of one part of a system, but only by increasing the entropy somewhere else. When you clean your room, you're using energy, you're burning calories, you're generating heat. That heat radiates into the environment. It increases the entropy of the air around you. The total entropy of the system, you plus your room plus the environment, still increases. You can't win. You can't even break even. The universe as a whole is always becoming more disordered. Let me give you another example. Ice melting. You take an ice cube out of the freezer. You put it on the table. It melts. Why? Because liquid water has higher entropy than ice. In ice, the water molecules are arranged in a very specific crystal structure. Low entropy. In liquid water, the molecules are moving around randomly. Lots of possible arrangements. High entropy, so the ice melts. Entropy increases. Can you reverse it? Can you make the water spontaneously freeze back into an ice cube? Not without a freezer. And the freezer uses energy. It generates heat. It increases the entropy of the environment. The total entropy still goes up. This is the second law in action. Every process that happens naturally, without external intervention, increases the total entropy of the universe. Heat flows from hot to cold, never the reverse. Gases expand to fill a container. They never spontaneously compress into a corner. Living things age and die. They don't unage and come back to life. All of these are manifestations of the same principle. Entropy increases, the universe is becoming more disordered, and there's nothing you can do to stop it. Now here's where it gets really interesting. The second law of thermodynamics is the only fundamental law of physics that has a direction in time. Think about it, Newton's laws, time reversible. If you film a planet orbiting the sun and play it backwards, it still obeys Newton's laws. Maxwell's equations for electromagnetism, time reversible. The Schrödinger equation in quantum mechanics, time reversible. Einstein's equations in general relativity, time reversible. All the fundamental laws of physics work the same forwards and backwards in time, and yet we only ever experience time moving forward. Why? Because of entropy. The direction of increasing entropy is the direction we call future. When you remember the past, you're accessing low entropy states. Your brain has records, memories of configurations the universe used to be in, but you can't remember the future, because the future is higher entropy, more disordered, less information. You perceive time flowing forward because you perceive entropy increasing. If entropy were decreasing, you'd perceive time flowing backward, but it's not, and you don't. This is called the arrow of time, and it's deeply connected to the fact that the universe started in a very low entropy state. The Big Bang. About 13.8 billion years ago, the universe began in an incredibly hot, dense, uniform state. You might think hot and dense sounds like high entropy, but it's not, because gravity is involved. For a gravitational system, a uniform distribution is actually low entropy. High entropy for gravity is clumps, stars, galaxies, black holes. So the early universe, smooth and uniform, was low entropy. And ever since then, entropy has been increasing. Structures formed, stars ignited, galaxies clustered, entropy went up. And it's still going up. Every star that burns is converting low-entropy nuclear fuel into high-entropy heat and light. Every black hole that forms is creating a region of extremely high entropy. The universe is becoming more disordered, and this process will continue forever until we reach the heat death of the universe. Let me explain what that means. The heat death of the universe. It sounds dramatic, and it is, but it's not a sudden catastrophe. It's a slow fade. Here's what happens. Right now, the universe has structure. There are stars, galaxies, planets, temperature differences, hot things and cold things, and whenever there's a temperature difference, energy can flow. Work can be done, things can happen, life can exist. But over time, entropy increases. Hot things radiate energy. They cool down. Cold things absorb energy. They warm up. Eventually, everything reaches the same temperature, thermal equilibrium. When that happens, there are no more temperature differences, no more gradients, no more flow of energy. Nothing can happen anymore. The universe becomes a uniform, lukewarm bath of radiation. Maximum entropy. No stars, no galaxies, no planets, no life, just photons, drifting through an ever-expanding void, forever. This is the heat death, and it's the inevitable fate of the universe if the second law of thermodynamics holds. Now, this won't happen anytime soon. Current estimates suggest it'll take around 10 circumflex 100 years. That's a 1 followed by 100 zeros. For comparison, the current age of the universe is about 10 circumflex 10 years, so we've got a long time. But it's coming, slowly, inexorably. Every process that happens, every star that burns, every thought you think is pushing the universe closer to that final state. You are contributing to the heat death of the universe. Right now, by existing, your body is generating heat, increasing entropy. You can't help it. It's the price of being alive. Life is a process that locally decreases entropy. You organize molecules, you maintain structure, but only by increasing the entropy of your surroundings. You eat low-entropy food, you extract energy, you excrete high-entropy waste. Net result, entropy goes up. This is true for all living things. We're all little entropy-generating machines, fighting against the tide, building temporary islands of order in a sea of chaos. But the sea always wins. Eventually, your body will stop functioning. The structure will break down, the molecules will scatter, entropy will increase, and the universe will take one more tiny step toward heat death. Now, you might be wondering, can entropy ever decrease? Locally, yes. You can build a house, you can freeze water, you can clean your room. All of these decrease the entropy of a specific part of the system, but they require energy input, and that energy comes from somewhere. When you use energy, you generate waste heat, you increase the entropy of the environment. The total entropy of the system, the part you're organizing plus the environment, always increases. This is the key insight. You can fight entropy locally, but you can't fight it globally. The universe as a whole is always becoming more disordered. Now, there are some interesting edge cases. Black holes, for example. Black holes have enormous entropy. The entropy of a black hole is proportional to the area of its event horizon. When matter falls into a black hole, it seems to disappear. Information is lost, and for a long time, this seemed to violate the second law. But then Stephen Hawking showed that black holes radiate. They emit what's called Hawking radiation, very slowly, very faintly. But over unimaginably long timescales, black holes will evaporate completely. And when they do, the entropy is released back into the universe as radiation. So even black holes don't violate the second law, entropy still increases. Another interesting case, the expansion of the universe. The universe is expanding, space itself is growing, and as it expands, it cools. The cosmic microwave background radiation, the afterglow of the Big Bang, is getting colder and colder. You might think this means entropy is decreasing, but it's not. Because the volume is increasing. Entropy depends on both temperature and volume. As the universe expands and cools, the total entropy actually increases, so even cosmic expansion doesn't violate the second law. Entropy goes up. Always, there's no escape. Alright, here's the big question. If entropy always increases, and the universe is currently in a state of relatively low entropy compared to where it's headed, why did it start with such low entropy in the first place? This is one of the deepest mysteries in cosmology. The Big Bang. The universe began in a hot, dense, smooth state. That smoothness, that uniformity, is low entropy. But why? Why wasn't the universe born in a maximum entropy state? If it had been, nothing would have ever happened. No stars, no galaxies, no us. So why did the universe start out far from equilibrium? We don't know. Some physicists think it's just a boundary condition. The universe started that way because it did. End of story. Others think there's a deeper explanation. Maybe our universe is part of a multiverse. Maybe there are countless universes, all with different initial conditions. And we happen to live in one where the entropy started low, because if it hadn't, we wouldn't be here to ask the question. This is called the anthropic principle. It's controversial. Some people love it, some people hate it. but it's one possible answer. Another idea is that the universe underwent a period of rapid expansion called inflation. Inflation smoothed out the universe. It stretched tiny quantum fluctuations into cosmic scales, and that smoothness is the low entropy we started with. But this just pushes the question back a step. Why did inflation happen? What caused it? What was the state of the universe before inflation? We don't know. This is the frontier of cosmology, the origin of the arrow of time, the reason the universe started in a low entropy state. It's a mystery, but what we do know is this: the universe started with low entropy. Entropy has been increasing ever since, and it will continue to increase until the heat death. That's the story of time, from order to disorder, from structure to uniformity, from low entropy to high entropy, from the Big Bang to the heat death. And you, right now, are living in the middle of that story, in a brief window where entropy is low enough for stars to shine and life to exist. Enjoy it while it lasts. So let's come back to where we started. Time only moves forward because the universe is dying, not quickly, not violently, but inevitably. Entropy is increasing, disorder is growing, the universe is slowly, inexorably moving toward a state of maximum entropy. Heat death, and there's nothing you can do to stop it. Every action you take, every breath, every thought, every movement increases the total entropy of the universe. You can create local pockets of order, you can build, you can organize, you can live, but the price is always the same: more entropy elsewhere. The second law is undefeated. It explains why eggs break but don't unbreak, why ice melts but doesn't unmelt, why you age but don't unage, why time flows forward and never backward. It's the most fundamental law in the universe, and it's the reason everything eventually falls apart. But here's the thing: you're alive right now, in this narrow window of cosmic time where entropy is low enough for complexity to exist, low enough for stars to burn, for planets to form, for life to emerge. For you to be here watching this, thinking about entropy, that's extraordinary. You are a temporary island of order in a universe that's sliding toward chaos, a brief flicker of structure in the long march toward heat death. And one day you'll dissolve back into that chaos. Your atoms will scatter, your entropy will increase, the universe will take one more tiny step toward equilibrium. But right now you're here, and that's beautiful. Not in spite of the second law, but because of it. Because entropy is low enough for you to exist, and high enough for time to flow, for change to happen, for life to unfold. So yes, the universe is dying, but it's dying slowly enough for you to live, and that is the most amazing thing of all.